This is a download from the BBC. To find out more, visit bbc.co.uk/Radio 4. If you've enjoyed this programme, you might like to try other Radio 4 podcasts, including Start the Week, lively discussions chaired by Andrew Marr, and a weekly highlight from Radio 4's evening arts programme Front Row. To find out more, visit bbc.co.uk/Radio 4.
Hello, I'm Robin Ince.
And I'm Brian Cox.
And this is the Infinite Monkey Cage from Manchester Science Festival. Since we were last on air, many things have happened, but the worst thing that's happened is Brian Cox's level of science celebrity is now so high that we actually can't afford him for most of the show. BBC budgetary constraints mean we can only afford 7 more words from you.
Only 7 words.
3 more words from you.
Oh dear. 1
more word, and we'll keep that word for a little bit later there. Perhaps you can use that word for looking at a shining thing and pointing. So for that reason, because we've basically got an emergency procedure, and we don't normally introduce our first guest this early, but we've got someone to replace Brian Cox, and it is the brilliant impressionist John Culshaw. Now, John, we're very pleased to have you here, and I know you can do his voice perfectly, and I know also, I spoke to you about a month ago and said, do the reading, learn the science, you'll be able to do him.
Yes,
that's where he just busks it, basically.
I've done as much of that as possible.
Good. Right, so this is going to be... You don't say anything, Brian. This is going to be... From now on, John will be playing the part of Brian, so I'll give you the first... Just a nice, easy starter. We'll start off on neutrinos. While we've been off air, there's been some kerfuffle over the idea that neutrinos might actually travel at faster than the speed of light, and thus the laws of physics will have to be rewritten again. So, Brian, can you explain neutrinos and what their superliminal travel may mean for causality?
Well, neutrinos are really wonderful and they're really beautiful and amazing. The amazing thing is that they're so small that they can't even be seen with the human eye, or even by the eyes of things that are really small, like a vole, like a flea, or even an ant. And the neutrinos are faster than light because, when observed, they appear to be weaving teeny, tiny, wonderful little rollerblades that mean they can go through the universe like it was a disco. And in the year 2000, there was a band called Oxide and Neutrino who did Bound for the Reload, but it wasn't very good, and it was quite hard to listen.
I'm going to have to stop you there. How exact was that real Brian Cox?
Nonsense.
Right. John, have you done any of the reading?
Vaguely. I just scanned over it. You know?
But John, John, I know that you're a very keen amateur astronomer.
Yes.
I mean, we first met on the Sky at Night 700th edition, wasn't it? Which was a real privilege to do.
Yes, it was. And Sir Patrick Moore was there. And he introduced you very magnificently. He said, "Welcome to the 700th Sky Night, where we shall be talking about the fountains of Enceladus. They shouldn't exist, but they do."
I tell you what, John, as well, the neutrino results, I mean, they may open up the possibility of time travel, a bit like Doctor Who.
Well, yes. Yes, absolutely, absolutely. I have reversed the polarity of the neutron flow, so the monkey cage should be free of the force field now.
And then one of the great challenges for theoretical physics is understanding gravity, quantum theory of gravity, which is a force that does indeed surround us, penetrates us, and binds the galaxy together. Doesn't it, John?
Yes, you must do what you feel is right, of course.
What if Alan Carr were...
Stop it!
John?
Do you know, I thought Higgs boson was a brewery.
Right, no, we'll get a grip now. In this series, we're going to be covering subjects as diverse as the origin of life, the science of sound, and, special Christmas edition, the physics of Christmas with jolly old Richard Dawkins.
Here's a shiny farthing. Now go and get the most secular turkey you can. No threat to you, John. I can only do 2 different people. That's it. One of them is me.
Yeah. But today, we're going to be talking about Manchester. We're going to be asking the question, what's the North ever done for us? Now, Manchester is a great city with a history of scientific discovery second to none, and certainly not second to Cambridge, I would say.
Yeah, if you ignore Isaac Newton, who I think had some role in modern physics, didn't he?
Do you do Newton?
My name is Isaac Newton.
All right. Science time. Joining us to discuss the history and future of science in Manchester are two of my colleagues from the University of Manchester. Matthew Cobb, who's Professor of Zoology, an expert on the sense of smell in maggots.
Which, of course, led to the classic joke, my maggot's got no nose. How does it smell? Through 21 smell cells, which feed into a complex series of glomeruli, which feed into projection neurons and the mushroom body.
Get on with it.
So were you the one who didn't get on? Look, let's not get involved in this now. Why don't you do something to help me? Anyway, so...
Oliver Hardy. He does impressions. Yeah. Let's go on.
Yep.
I'll challenge you. Go on, Gregor Mendel in the style of Oliver Hardy. How's that?
Yeah, I can do that one. There. Why don't you do something to help me shell these peas? What do you mean, recessive? Our other guest from Manchester University is Jeff Forshaw. He's a professor of theoretical physics and is the man you go to when Brian Cox is away looking at things in a hot place. So you've been very, very busy lately, of course. He's known in the bars around Manchester as Mr. Pomeron because he interacts very strongly, but being a northerner, he's colourless. Well done, those of you who understood that joke. And if you didn't understand that joke, can you tell me what it means later on? I have no idea.
And this is our panel.
Jeff, I want to start with you. Now, Manchester, the idea that it is this kind of this hub of scientific knowledge, is there something different about the Manchester way of approaching science compared to, say, what was seen as the traditional old-fashioned way that Oxford and Cambridge had before the 19th century?
Yes. This idea of a Manchester attitude, it's in popular culture almost, and it's easy just to refute it and say it's nonsense. But there are two different ways of doing fundamental science. I'm speaking as a particle physicist. One is the kind of the string theory approach, the kind of Platonic ideal, the idea that you kind of think about the way the world is and through this very, very pure process arrive at these conclusions about how things work. The other way of doing things is to just get stuck in and just do it, right? See, I've got a little piece here, right, which I can read, written by Freeman Dyson, a famous theoretical physicist, who wrote an essay called Manchester and Athens. He said these are the two great cities in civilization. He says that it was the anti-academic, anti-establishment brashness of Manchester that made a fertile ground for the growth of science. Manchester brought science out of the academies and gave it to the people. And in the new environment that Manchester offered at that time, I think it's out of that. It was fertile ground for this different way of doing science, this earthy way of doing science.
And Matthew, I mean, you're both of you professors at Manchester. Do you think we can still claim I shouldn't really say just Manchester. I mean, I suppose there's other bits of the north, isn't there? But
I have heard talk of other areas. A man once returned from a place called Preston. He was very bedraggled.
but you think that atmosphere of non-conformity, which was clearly there in the history of this city and the north, is still there to an extent? So is that pushing it a bit as a professional academic?
No, it's very, very different here. I think in terms of the way we work, in terms of integrating whole areas, and the size of what we have as a faculty, which just means there's no departments, there's no separate structures between people. So if you meet somebody in the coffee lounge or you hear them giving a talk and you think, oh, I could use that technique, then you're actually encouraged to collaborate. And this extends outside of our part of the university and into things like the people working on the colours in dinosaurs. A lot of that work has been done here in Manchester, but also using machines around the world. And it's that integrating approach to science using both very, very simple techniques and very complicated techniques to address some of the most interesting problems.
I can't let that go. Matthew, you just said working on colours in dinosaurs.
Yeah.
As the professional idiot on this show, anything about dinosaurs, I want to... So can you just tell me more about that?
So we now know that certainly half of one branch of the dinosaurs, they were covered in feathers, so all that business in Jurassic Park when you see the velociraptors doing all that and they're turning the key and they were about half the size, they basically look like big chickens. And we've been able to work out from looking at the way that the light is reflecting in the fossils that the colours they must have had, so creamy with some orangey bands on it.
A bit 70s, really.
Had loon pants as well.
I was going to ask, John, as someone who hasn't grown up to be a scientist, when you were growing up in this area, did you get a sense of the kind of scientific achievement, of the fact that there was something different here about the mixture of the industry, the science, and that kind of achievement?
Yes, absolutely. I like what Jeff was saying about the no-nonsense approach to science that you would get in Manchester. I wish some of the Apollo launches had been launched in Manchester. The countdown would have been wonderfully no-nonsense. Right, 5, 4, 3, 2, 1, off you go, off you pop to the moon. I always wish that, in many ways, Fred Dibner had become, an astronomer, Because it's like, you look at Saturn and Saturn's rings, and like some of them where you get up close are about as big as bricks,
It's not
Brian,
it's not far off me, actually.
Yeah, that's what I was thinking.
It's very close.
I saw your face when you started to go, I wouldn't have a career.
But I wanted to ask Jeff, actually, could you just step through very briefly some of these great discoveries that have characterised Manchester from back in the 19th century and onwards?
Yeah, and I actually was guilty of this, thinking that, maybe Manchester's great scientific discoveries were in the past. But actually, they've been a steady stream since 1800. So 1800, John Dalton came up with the first serious idea that things are made of atoms. That was here. And his student, James Joule, 50 years later, came up with the law of conservation of energy, the first law of thermodynamics, which is, these are profound discoveries, the equals mc squared of its time. 1911, Rutherford is in Manchester and has discovered that solid matter is essentially empty, that all the mass in an atom is in a tiny, tiny part of it, right in the centre. So tiny, in fact, if I zoomed in on an atomic nucleus and made it about the size of a ball, then the electrons orbiting around it would be orbiting away at a distance of 10 kilometres away. And he discovered that essentially all the mass is in this tiny little football and that everything else is empty. So it's a miracle that, we don't fall through the floor. It demanded an explanation. What is it that puffs out an atom? What is it that gives it its size? That's the beginning, really, in earnest, of quantum theory. 1950, just a few years later, so these are kind of coming in 50-year steps, these great discoveries that really have changed the world. Radio astronomy is invented in Manchester. And Jodrell Bank.
I'm going to say it's our audience. Any radio astronomers in the house? It's just, you don't get that very often, do you?
Other audiences react like that to Westlife, but not here.
Let me finish.
So, yeah.
The best is yet to come, right? So at the same time that Lovell was making Jodrell Bank, we were building the world's first computer. And 60 years after that, we've got the discovery of graphene, which is very likely to change the world. Manchester won the Nobel Prize last year. Kostya, Novoselov and Andrei Geim discovered it. Brilliant.
Very Manchester name, so
brilliant.
You'd always hear in Cheadle Hume.
Its properties are remarkable. It's something that it's 200 times stronger than steel. I think I read on Wikipedia that a cling film thick layer of graphene could support an elephant. So it's one of the strongest materials in the world, and it's much lighter, much stronger, much harder, much more flexible than steel. So it's hard to believe that material, which recently discovered here in Manchester, is not going to have a world-changing effect.
Matthew, it sounds quite physics-heavy at the moment.
It does, doesn't it? Not good.
So address that, if you'd like to.
Okay, well, I think even using physics, we can start with Turing, who was missed off your list of great Manchester events. So Alan Turing, who most people will know in terms of his work during the Second World War, helping to crack the Enigma code, he came to Manchester just after the war and started working on the newly built computer. And then when he was here, he started to do two quite remarkable things. Firstly, he started wondering about what consciousness is and whether we could actually embody it in a machine and how would we know that. So he wasn't doing any experiments, he was just sitting down and thinking about it. And his idea of the Turing test, that if you could ask a machine, you'd have a room, you'd got two responses, one from a machine and one from a person. And if an observer couldn't tell the difference between the machine's answers and the human's answers, then you'd end up saying, well, that machine is effectively conscious. So it's really important in terms of development of ideas of artificial intelligence. And what I'm particularly interested in is at the same time, he started trying to understand how cells and organisms develop. which, when I first heard about it, I thought this kind of typical maths arrogance, that a mathematician thinks he can work out all this complicated stuff, just like physicists think they can work it all out, and then the chemists think they can work it all out. And you know what? Life is really complicated, and living things are really complicated in a ways that you people just can't even begin to understand.
Are there any molecular biologists in the house?
You know, you have laws in physics. You know, you can write down equations. We have a few equations, but there are generally exceptions to them, which are what makes biology so fun. But what Turing started to try to understand was, how do organisms grow? So you probably think that your genome is a blueprint with a set of instructions for making stuff, like a finger. Well, it's not. There is no gene for a finger. So when you're developing, when you were an embryo, you had kind of lumpy little clubby limbs at your end of your arms. And then some of the cells started to die. And that was the gene telling them, die back. And then, as those cells die, you start to get the development of your fingers. So there's no gene for finger. What there is a series of genes that at various points in your body will tell cells to die to enable form to appear. And Turing, who didn't know any of that, and didn't know anything about DNA because it hadn't been discovered, started just thinking, well, how does a cell know what it is? How does a cell know what to do? It must be told that by its neighbours. And that could be quite straightforward, that a series of neighbours will send a chemical message, which Turing called a morphogen. They'll send that message to the cell and say, die, die, and it will then die back, and you end up with fingers. Or it could be something much more complicated. So he tried to work out, using a series of equations, using the baby computer, to try and understand how this actually worked. And sadly, he committed suicide before this work could be fully developed. He published it in 1952, and nowadays biologists are trying to apply that. They're trying to apply that method to the latest data on how organisms develop, the latest molecular genetic data about how cells decide what they are. And at least in some cases, he was absolutely right, and I think it's quite remarkable genius that he had.
John, do you ever think that, again, as the other non-scientist on this show, we've just heard about the fact that most of what makes everything is empty. In fact, it's nearly all empty space. Everything that makes us is empty space. We've found out that fingers are basically there, messages from genes going, just die, die, die. Now, this, to me, is both wonderful, but also that sense of cosmological vertigo that, you know, when you hear, so it's all empty space, and you think, well, it can't be. That's ridiculous. Do you ever get a certain kind, almost a fear that when you have that level of rationalism and possible truths?
Oh, yes, I think so. Anything that makes the world more of a place of wonder is fantastic. I was just listening to your description there and thinking, my goodness me, this is how Keith Chegwin was formed. It makes him seem more impressive, you know. John McCririck was made this way. It sort of makes them seem more impressive.
No, he was different, wasn't he, John McCririck?
Yeah,
it was entirely different biology.
Something went slightly wrong there, yes.
He was cloned from Tweed on the first, yeah. They started with McCririck, then they did Dolly the Sheep. It was that order.
I just love the way that once you start discussing things like this, you get to a certain point and your brain starts to get really confused and you can't go any further, like the tiny particles that Jeff was talking about. Is it believed now that we have discovered all particles, or in 1,000 years may we be aware of even smaller ones? Is that journey into microscopics going to keep going on? Is that infinite as well as the universe in that direction?
That is a brilliant question. In the sense that the essay that I was talking about from Freeman Dyson is called Infinite in All Directions. The idea that things just, you know, that tiny particles might be made of something is, I mean, it's a natural thing to think about. It doesn't have to be that way, of course. It could be that there are elemental building blocks, and for which it makes no sense even to talk about their content. And the Large Hadron Collider is testing that idea. And it may well be that, you know, we'll discover that things are made, have got substructure.
And that could, in fact, remove the necessity for the Higgs particle. So one way you can generate mass in the universe is not this fundamental thing called the Higgs particle, but have substructure. And that the history of particle physics actually goes down that route, doesn't it? It's basically finding substructure which explains these more
every time we've looked,
phenomena.
we've found something inside of the little things.
Talking there, obviously, from the approach of life sciences and then physics, where, to me, you know, with a lot of advances in biology, there then are a lot of criticisms. A lot of people become furious and they make placards. You know, that moment there when Darwin finally published there was fury. And yet, coming up with Ernest Rutherford saying, well, basically, it turns out nearly everything's empty space. People just go, oh, that's fine, we'll move on. And that, to me, seems to have some real ramifications for what you believe in. Why is it that physics seems to manage to pass by a lot of those kind of arguments from the placard wavers, whereas biology gets it in the neck?
I mean, physicists believe that things are empty, but they're not. You know, it's not. Tap your head. It's solid. I mean, this is just stupid. So if you're interested in higher things, not subatomic physics,
higher things than atomic physics.
If you're interested in organisms and how they interact in the planet...
It's just mess, that. It's just overlying the fundamental beauty of the universe. They're emergent phenomena that cause all sorts of problems.
Well, exactly. They're causing problems, and that's why it's interesting.
There is actually... I mean, this has got nothing to do with Manchester at all, but there is a debate we've had many times on Monkey Cage about whether complex structures such as human beings can, in principle, be derived from these basic laws. And we get a lot of opinions either way, actually, on the show. So, Matthew, what's your opinion there? I mean, essentially, do you think that if you had a sufficiently good understanding of the basic laws of physics, you could derive a person?
No. Okay, so I'll give you an example. Go back to the genome. Read the genome of the chicken. We sequence the chicken genome. Where in there does it say that a male chicken will go cock-a-doodle-doo? There's no immediate it's in there, but it's not in there. So it's an emergent property, exactly as you said. And those emergent properties, precisely because they're not linear, you can't simply derive them.
I mean, or if you had a sufficiently powerful, a universal Turing machine, let's bring it back to Manchester, a sufficiently powerful computer, you could, in principle, derive the map of life forms you could have.
I don't know. How would you know? Wouldn't you be rerunning the whole universe? Aren't you asking, in fact, for this big machine to be rerunning the whole universe and all the potential alternative developments there were there? I don't know what the answer to this. I don't know how to know.
It's at times like these we need Alan Moore back on this show, because he's always got an answer for that. I mean, John...
Or Alan Carr. I don't know what's going on.
What do you think, Alan? Determinism...
Well, I want to know, why do all organisms have to be carbon-based? Maybe silicon or some other form of basis.
Yeah. Right. I think you're dead right, Alan. That's exactly possible.
I want to go back to that Manchester thing and just, we're talking there about what Alan Turing did when he came up here. We're talking about the incredible discovery of Ernest Rutherford. I mean, are we saying that it needed to happen here with the methodology that was going on, that it would have taken longer if we had remained in the kind of, as you were saying, the more ideal version of science and scientific ideas that were going on in the traditional Oxford and Cambridge environments?
I think it would be stretching a point to suppose that the things that started and characterised science in Manchester in its early days driving what's happening now. I think that's not right. I mean, what that certainly did, though, was develop a momentum which has continued to this day, and a heritage which people working here are inspired by. But I don't think it's the case that this kind of mank attitude, the scientists in the physics department aren't all walking around, baggy trousers or whatever a mank attitude is, right?
It's not. A scientist with a mank attitude.
I see the biology department as Morrissey-esque, and kind of the physics department is more Happy Mondays-esque. Yeah, that's the way that
It's an international arena now. I mean, Andrei Geim and Kostya Novoselov, probably little influenced by the
Happy Mondays.
The Happy Mondays.
Yeah. One of them does the experiments, the other one just dances in the background. It's a beautiful mix.
John, I'm fascinated by this idea of a mank physicist.
Exactly. If Einstein had been from Manchester, it would have been, right, you've got E, right? And what that equals is like M and like C and squared, and that's it. That's my theory. I'm having it. Sorted. We're not going to top that for years.
I know Matthew, actually, you tell me a fascinating story about Manchester's... We've said that the North, in particular, had this particular attitude different from Oxford and Cambridge. But you tell me the story about some discoveries about moths that required Manchester's less beautiful side.
Well, yeah, I mean, so one of the most important proofs of the principle of evolution by natural selection was first observed in Manchester, where during the Industrial Revolution, the streets got terribly dark, all the trees got dark, and amateur entomologists who were collecting moths noticed that they started to find very few of the light-coloured moths and lots of the dark-coloured moths. This is called industrial melanism. And so the dark form, which in the middle of the 19th century was about 2% of the population, by the end of the 19th century had gone up to about 90%. So it's this massive change in only 50 years in the colour of these two kinds of moth.
You want to say, well, they're just dirty, don't you? But I know that. Well, give them a wash.
Give them a wash.
That's very, very fast for an evolution.
It's incredibly
Normally
fast.
it takes millions of years.
Fast. And what's really interesting, of course, is now we've got clean air. They introduced the Clean Air Act in the 1950s, and it's now switched back the other way in another 50 years. So we can see this change driven by industrial pollution leading to change in the two colours. And we now know, people have been able to identify the genes or probably the single gene involved in coding for this darkness and exactly why it happened. It wasn't only in the moth. There was about 70 other species of insects showed this industrial melanism. So that's a really important example of how natural selection can actually shape evolution, shape animals and change their shapes and colours very, very quickly.
How many generations is that? What's the
I don't know. It's going to... I'm a maggot man. I'm not a moth man.
What a great superhero that would be.
Maggot man.
Yeah, that's a Stan Lee needs to invent that superhero, maggot. Could I ask a maggot question? I have a maggot question.
Okay.
In the 1973 Doctor Who story, The Green Death.
Yeah.
Now, there was some industrial toxic waste,
That's
and
right.
it affected some maggots, and they became giant maggots, and John Pertwee had to stop them. Could that actually happen?
Yes.
Could that happen to... Could maggots...
Come to my lab.
One day I will rule the world. Now we actually asked the audience as well a question to find out if we could get to the bottom of if the North had something very special that made it better for scientific discovery. What's the North got that makes it so good for scientific discovery? The North has always embraced pies, and gravy tea.
I've got one here, which from Twitter, it says, the desire to discover something that will stop it raining.
This one from Blue Lozenge Bear. The North has got my girlfriend. She's very experimental.
This is rather succinct. What's the North got that makes it so good for scientific discovery? Deirdre Barlow's glasses.
What about this one?
Do her, John. Do you do Girolo?
No, but I can do can. Yeah.
Here's one, a happy one. A grimness that inspires the need to find the point of it all.
So there we are. Next week we're going to be looking at balance and asking, is it only fair to give everyone a platform, however wrong they are? So we'll be joined by the President of the Royal Society, Paul Nurse, and the week after that we'll be dealing with all the complaints from people who say that we were very one-sided in our handling of the idea that the moon is a hollow spaceship. There really is a book about that, by the way. They've gathered all the scientific evidence, and then on the second page they start to make things up. So, thanks to all of our guests. Good night, Jeff Forshaw. Good night from Matthew Cobb.
Good night from Brucey.
Nice to see you, Entropy.
Good night from... It's good night from Patrick.
Yes, and we shall be here next week. Until then, very good night.
It's good night from Tom Baker.
Yes, or it might be hello, although that hasn't happened yet.
It's good night from Russell Crowe.
Look, this is going to take a while, so thank you very much for listening. Goodbye.
And they're really beautiful and amazing. The amazing thing is that they're so small that they can't even be seen with the human eye, or even by the eyes of things that are really small, like a vole, like a flea, or even an ant. And the neutrinos are faster than light because, when observed, they appear to be weaving teeny, tiny, wonderful little rollerblades that mean they can go through the universe like it was a disco. And in the year 2000, there was a band called Oxide and Neutrino who did Bound for the Reload, but it wasn't...
I know you can do his voice perfectly, and I know also, I spoke to you about a month ago and said, do the reading, learn the science, you'll be able to do him. That's all, he just busks it, basically.
I've done as much of that as possible.
Good. Right, so this is going to be... You don't say anything, Brian. This is going to be... From now on, John will be playing the part of Brian, so I'll give you the first... Just a nice easy starter. We'll start off on neutrinos. While we've been off air, there's been some kerfuffle over the idea that neutrinos might actually travel at faster than the speed of light, and thus the laws of physics will have to be rewritten again. So, Brian, can you explain neutrinos and what their superliminal travel may mean for causality?
Well, neutrinos are really wonderful, very good, and it was quite hard to listen.
I'm going to have to stop you there. How exact was that real Brian Cox?
Nonsense.
Right. John, have you done any of the reading?
Vaguely. I just scanned over it. You know.
But John, John, I know that you're a very keen amateur astronomer.
Yes.
I mean, we first met on the Sky at Night 700th edition, wasn't it? Which is a real privilege to do.
Yes, it was, and Sir Patrick Moore was there, and he introduced you very magnificently. He said, "Welcome to the 700th Sky Night, where we shall be talking about the fountains of Enceladus. They shouldn't exist, but they do."
I tell you what, John, as well, the neutrino results.
Things have happened, but the worst thing that's happened is Brian Cox's level of science celebrity is now so high that we actually can't afford him for most of the show. BBC budgetary constraints mean we can only afford 7 more words from you.
Only 7 words.
3 more words from you.
Oh dear. 1
more word, and we'll keep that word for a little bit later there. Perhaps you can use that word for looking at a shining thing and pointing. So for that reason, because we've basically got an emergency procedure, and we don't normally introduce our first guest this early, but we've got someone to replace Brian Cox, and it is the brilliant impressionist John Culshaw. Now, John, we're very pleased to have you here.
This is a download from the BBC. To find out more, visit bbc.co.uk/Radio 4. If you've enjoyed this programme, you might like to try other Radio 4 podcasts, including Start the Week, lively discussions chaired by Andrew Marr, and a weekly highlight from Radio 4's evening arts programme Front Row. To find out more, visit bbc.co.uk/Radio 4.
Hello, I'm Robin Ince.
And I'm Brian Cox.
And this is the Infinite Monkey Cage from Manchester Science Festival. Since we were last on air, many